So I'm going to share my screen and I'm going to do a review. And let me see if I've got the right one here. I think I do. Yes. And this will be, I hope, a 15-minute review of the entire course, and I'm going to go very fast. So this is the 8th lecture, review and discussion. And especially I want to think about peak oil energy return on investment, limits to growth, and what that means for our current economic situation. Okay, the first lecture we had, the idea was to understand the importance of energy in the earth around us, how general it was, how it wasn't just in the physics lab, how it was everywhere. That every time I do the dishes, I think about energy, the energy of hot water versus cold, the energy of my scrubbing, the energy of the detergent, and how that works and so forth. So unfortunately, energy is usually taught in as some part, some entity in physics, or in ecology, only one chapter out of 18 in the book. But in fact, it's pervasive in natural selection. It's pervasive in our activity as organisms and so forth. And that in the past, people didn't understand energy at all, but they were, except in a certain way they did. And many of the old gods were about energy. Prometheus bringing energy to humans and so forth and so on. And the origin of our understanding, our modern understanding of energy, started with this guy, Sadi Carnot, a French military engineer, and who understood that it wasn't just heat that was important, but a gradient in heat to do work. And then James Prescott Joule, who understood the importance of the way in that you could measure very carefully the thermal equivalent of physical work. He'd drop a weight over a pulley, and this paddle wheel would turn in water and the temperature would rise. And so he could get what he called the mechanical equivalent of heat, but I think the heat equivalent of mechanical. And then Thomson, Clausius, Helmholtz, and Kelvin put it all together, Thomson maybe especially, this guy, and came up with the laws of thermodynamics, which were so critical to understanding energy. The first law of thermodynamics is the quantity of energy is conserved. Now remember, this is only because we can measure all energy in terms of its heat. So when you're begin and you end, the heat is conserved. But the second law says the quality of energy is not conserved. At each transformation, some energy is lost to low gradient heat. And we go back to Carnot, and it's heat that doesn't have enough of a gradient to do work. It's heat that's just 1 degree above its surroundings, and you can't do any work with that. And that's the important thing. And what that means is sooner or later, the universe is going to run out of energy, supposedly. That's going to take a long, long time. And in a much shorter time, our special energy reserves will be gone. Okay, second presentation focused on the early life and Earth environment, the particular role of the sun, evolution of life, and the most important things that happen. So here's the sun, and here's a, I should put it on the display. Excuse me for a second. What's happening here? Here. So here's the sun. Here's the sun running the Earth thermal machine. And from our perspective, there's solar input, which is we call free energy, it's available energy, and it goes to unavailable energy, that's low temperature gradient energy. And life and earth and whatever is just a little paddle wheel stuck in that flow of energy. It captures energy over time and then uses it to run the machinery of the earth and the machinery of life.
Hey,
Quite amazing.
Charlie, I'm
And
going to interrupt for a second. I
yeah,
think you're
yeah.
going to want to put it on presenter view because we're seeing the information on your next slide, and I think for the purposes of your recording, you wanted to have it be just full screen for people.
What do I do now? I thought I
That's
was.
good.
Presenter view.
Where
Oh,
do I find that?
in your controls for PowerPoint, under play, slideshow. I think it's under
Oh, I
slideshow.
can't hear you. You don't have your thing on.
Oh,
What do I click on, Ann?
Okay, down at the bottom, all
Yeah,
the way to the right before you get to the slider, there's a,
yeah, I thought I did that.
okay.
Let's try again. Now there's I don't know. How about now?
Yeah.
um,
Ann, is it okay?
well, it's okay. I'll just fix it in the video editing. So go ahead.
Okay. I mean, can you see blue-green algae?
Yeah.
Ann?
Yes, we also see your next slide. It's okay. I'll fix it.
Okay. So so this magic that green plants figured out to take water and CO2. Now, the important thing from our perspective is there's no energy in water. You can't burn it. It's burned in a way. It's hydrogen that's already oxidized. The electron is at rest. And same with 6 CO2. But the magic that plants figured out is to rip the water and the CO2 apart and recombine them as sugar, C6H12O6, which is usable energy, and this waste product, oxygen. And this oxygen turned the atmosphere into an oxygenated environment, which you can see in these rocks from Glacier National Park. They're the same materials, the gray, green below and the red above, but but in the interim, at that margin, the atmosphere turned to oxygen and the iron in these rocks rusted and turned red. That's just rust. And the whole earth went from an anaerobic environment to an oxygenated one, which at first was very, very toxic for life. And then life learned to exploit through mitochondria, and all of this amazing evolution took place. And periodically, the clock was reset with a big meteor striking in southern Mexico, for example, and wiping out the dinosaurs except for the birds, and opening up opportunities for for these guys, for humans. And so here's Raymond Lindemann and Howard Odom. This was the end of that lecture. Figured out how to measure this energy flow in nature. Here's a picture of yours truly with a bunch of students out in the stream, and we do this every fall. We do a study of the flow of energy through one of these lovely little streams in upstate New York, and with the whole teams figuring out how to measure energy flow through an ecosystem. And then we learn how to make models of it. Third lecture, evolution of mammals, proto-hominoids, that means early humans, and our own species, and the increased exploitation of energy by humans and evolution of agriculture. All of this is about the evolution, which means gradual change, both natural selection and genetic evolution, and also cultural evolution of our species being able to exploit more and more of nature as figured out basically by Charles Darwin. For example, the evolution of our skull went from a flattening of the face as we became eating more plants mostly over time. And as you can see, an enormous increase in the size of our brain. Why? There was natural selection for being able to think. For whatever reason, it seemed it led to these guys having more surviving children till we have, good Lord, 8 billion of them. And it's all about energy, from spear points and fire to whatever it is that we're doing. And here are some of how our ancestors lived. These are modern people, but representing hunter-gatherers, and still doing quite well in Africa. Some of them following their ancestors' lifestyle. Very, very interesting to me. Okay, humans then came out of Africa. We found just in the last week that humans in Europe, and many of our ancestors, are more closely related to East Africans than East Africans are to West Africans, or East Africans are to South Africans. Just in the last week, we seem to have discovered this. And humans, of course, went all the way down through the Americas and had a marvelous time with lots of stupid animals that they could easily spare for thousands of years. Then something came on that really changed the energy picture for man, and that's for humans, is the evolution of agriculture, which we think of as taking place in the Middle East, basically, but actually place kind of simultaneously in these different green areas on this map, different parts of the world. I don't know why they kind of happened all at the same time, but that seems to be what happened. Okay, in humans, we think of genetic engineering as new, but this is what happened during the last 10,000 years, that people in Mexico, I guess you'd call them Native Americans, took this little plant on the left and kept what was the most productive of them over time until we got what we have on the right, modern day corn. Before we had any understood genetics, they just kept the biggest plants and bred them, and then kept the biggest of their children, and here we have corn today. Okay, lecture 4, Industrial Revolution. Here's an early James Watt steam engine with a big chamber over there. And the critical thing that James Watt had was that he would inject steam. He could have a port on either end with the steam going in during the upstroke and steam going out during the downstroke, and the converse on the other end. So this made a tremendous difference in the world and led to all kinds of intensive manufacturing. And somebody in the class was really scared about those dresses and gears, and with good reason. People got really hurt until people understood to cover up those straps, for example, with covers, steel covers. My hero in much of this is William Stanley Jevons, who came up with Jevons paradox. As you make things more efficient, we use more of the resource, and wrote about the coal question, that England was going to run out of coal within 200 years, which indeed has pretty much happened. 5th lecture on peak oil, energy return on investment, limits to growth. And I asked whether this fellow, M. King Hubbard, might be, whom I knew pretty well, incidentally, at one time, who was came up with the idea of Hubbard curve, that the use of a resource over time would increase exponentially, reach a peak at roughly half of the use of the resource, and then would decrease on the other side. This is a Hubbard curve, his first one that he did. He was a little bit underestimating conventional oil, and also he had no idea about unconventional oil, what we call fracking, which is adding, and Alaska, which he said, I think there might be oil up there, but I don't know, which has added a shoulder on this, but we're now declining on the far side. Let's see, we're now at 2020. So we've made it, it's been kind of flat till now, and now it does seem to be decreasing, but people can argue. Okay, in my own work with Jean Larrière and Roger, having a senior moment here, and Roger says that the official estimates of oil reserves, which are the brown line, are increasing, but they do it incorrectly. I should make this paper available on the site that we have, and the actual reserves that we had are declining rapidly. And we're actually in deep doo-doo with respect to oil, and people have no clue. These are three estimates that were made by Stephen Moore et al. And other people have done studies like this of all of our fossil fuels. And the blue is coal, and red is various kinds of oil, and the green is gas. And this is a low estimate, which I believe is closest to being correct, but I'm not sure. This is a median estimate that still has a peak before 2050, well before 2050, and a high estimate of fossil fuels for which I see no evidence, but that has a peak around 2050. So people who are alive today, no matter which of these estimates is correct, we'll take the median one, are going to have to deal with a constricting energy supply of all energy, not just oil, but especially oil. Gas will be a little bit longer, and then we'll see. This idea of the limits to growth that's associated especially with Donella and Dennis Meadows, and was really the brainchild of Jay Forrester, was published 50 years ago, and is pretty much right on in its predictions. And people don't understand it. This is basically a good representative of what we know today, what we can measure today. And while everybody is all worried about CO2 and climate change and everything, I and some few others are more worried about depletion as something that will impact human culture. And it's especially scary because we don't understand the political and social implications of this. For example, and this is just looking at what we do. This was a study that we published in 2009, and we have the economy here, which takes energy out of the ground, out of the world, and pumps it into the economy. And the question is, to get this energy to run our society, how much energy, the top dark blue line, do we have to invest into getting it? Now, we also have to invest into infrastructure maintenance, and then we have discretionary investment. Let's build a new movie theater, a new building, or a new whatever, and a new road. And so all of our GDP goes either into investments or consumptions. And we have staples, food, shelter, clothing, what we have to do, and discretionary. This is what it looked like in 2007. And projecting, this was our projections at the time, in that we would have to put more and more energy into getting the energy as the energy return on investment declined to get the same input to the economy. This appears to be true, which will require more energy here and squeeze out discretionary spending for both consumption and investment. People will see that as inflation, and that makes it politically unstable. Going to 2050, if EORI continues to decline, then it's not looking like a very wealthy future, because we have to put so much of our economic activity in just to getting the energy to run it. Okay, lecture 6 was conventional economists, and we talked about mercantilists, physiocrats, classical and neoclassical economists. And I note all were focused on the main economic energies of their time. Mercantilists, wind. The wind that moved sailing ships was critical to them. Physiocrats focused on land. Land was valuable. The English gentry had land. They were the wealthy ones because it intercepted the sunlight that ran the forests and the agriculture and the grazing lands of the time. That's what was the main energy input to the economists of the time. Classical economists focused on labor because the actual activities of human muscles was what was the main operation in as we invented manufacturing centers. And neoclassical economists focused on capital. And you might say, well, capital isn't energy, but capital is the means by which fossil energy was used. It's very important to understand that what is considered and taught as economics today is only one of a variety of ways that even economists thought about economics. It's almost an accident we think about economics as we do. All right, the most important economist, Malthus, who said the population, blue, would grow faster than the resources. Adam Smith, The Wealth of Nations, very, very famous. People think he was in support of business, and they use his one quote about how free enterprise makes it's not from the benevolence of the butcher, the brewer, the baker that we have our dinner, but from their own self-interest that provides the best situation for all of society. Adam Smith said many things. That was only one of the things that he said. Karl Marx, widely misunderstood. The birth of neoclassical economics by solving the diamond versus water paradox, and including Stanley Jevons, by the way. But that began the marginal revolution in the near abandonment of classical economics. And the idea was marginal utility. This was the critical thing. The first liter of water was worth everything you had, and the 100th liter much less, and the 1000th liter ho-hum. Okay, and let's not forget John Maynard Keynes, who talked a lot about how government intervention could smooth out the bumps in capitalist economy, and in fact, it did. Not until 1973. Lecture 7, the last week, why we need biophysical economics, and that conventional economics doesn't really understand this basic two pictures. This is a 33 horsepower harvester. Good one, I guess. And they're the 30, well, they're actually mules, but 33 horsepower, and you got 5 people running it, plus the stable boys, and you got to get the forage for the mules and so forth and so on. And this is what oil has meant, or fossil fuels, but oil in particular. Here's a 200 horsepower, 7 times bigger, controlled by one person. And of course, whoever built the harvester and pulled the oil out of the ground, et cetera. I mean, those things you'd have to do a little more complicated analysis. But this is why economics work. Whatever any idea you have about what economics is, if you pull out more oil out of the ground, You can make it work. And that's what we've done. And I say we need to focus on the energy, not on the economic ideas. So this basic idea of neoclassical economics, that economics is just a cycling between firms and household, is a main fairy tale about the economy. This breaks the laws of thermodynamics, has no energy input or degradation. It breaks the law of conservation of mass, and it has not been tested in using the scientific method. And we want to replace that with this being the minimum diagram one could have of how an economy works, starting with the energy sources and then the raw materials and the human steps of exploitation, processing, manufacturing, and consumption. That's an economy. There's an antidote to all of the misinformation above. It's called biophysical economics. There are various societies that deal with this. And we have our introduction to biophysical economics by Hall and Klipgard, who is an economist. Questions?